Up until now, we've been looking at polynomial functions that have been generally factored so that we could identify the roots of that polynomial very easily. But what do we do when we look at a polynomial that's not already factored? And that's what today's lesson is about, finding the rational zeros of a polynomial. We have this idea here where if we are given any type of polynomial, then we can use the P over Q theorem to identify possible factors of this polynomial. So let's just kind of start by identifying what on earth are we talking about by P and Q. So the P value is going to come from the constant, which is at the end of my descending polynomial, and the Q is going to come from the coefficient of the leading term. So in other words, this is P, and let's see, this over here, this first term would be Q. So to find out what the zeros are of this, we're going to go through and we're going to just kind of go through a couple of steps. First, let's determine what is the degree of my polynomial. The degree of my polynomial is a third degree polynomial, and that tells me that I will have at most 3 real roots. So my third degree polynomial says I will have at most 3 real roots. At most 3 real roots. 3 real roots at most. That's important. I may not have all 3 of them, but I will have at most 3. And how do I find those possible roots? Well, we're going to first identify the factors of P. So all of the factors of 6 would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So we're just going to make a list of all the possible factors for the number 6, and we're going to do that again on my Q term, which looks like plus or minus 1, plus or minus 2, right? Those are all the factors of the number 2. Now, to find out what the potential zeros are, we use this idea that I can take the ratio of the P values over the Q values, and those could be possible roots for my polynomials. So we're going to make another list here that looks like P over Q. So if I have, the P's are in the numerator, so I could have 1 over 1, so I would have plus or minus 1, and I could have 1 over 2, so I would get plus or minus 1/2. Let's move to the next one. 2 over 1, so I have plus or minus 2. 2 over 2, which is 1, so that's repeated. Now we do 3 over 1, plus or minus 3, and then 3 over 2, plus or minus 3/2. And finally we have 6 over 1, plus or minus 6, and 6 over 2, which is really just 3, so we don't repeat it. So what this says is that we have possible roots occurring at plus or minus 1, plus or minus 1/2, and so on for all of these roots. Now I could take each of these possible roots from this list that I just made, plug in that value for x in this equation, and solve, and I would try to, or simplify, and that would tell me whether or not I have a potential root. But instead of doing that, we're going to test this using the table function from our calculator. So I'm going to go into my calculator and I'm going to put this equation into the y1 graph spot. Now I've come to my y equals on my graphing calculator. Let me pull it back up. I came to the y equal on my graphing calculator. I have put in this polynomial that we were just discussing, and I'm going to use the table function to test these possible roots here. To do that, I need to set something up on my table function. So I'm going to click second window, and I am going to arrow down until I get to the independent variable. I want this independent variable to ask. I want to set it to ask, and that way it's going to ask me for an input for this x value. So we have it set here. I'm going to now go to second graph, or pull up the table, and you can see that the table is not populated because it's waiting on me to tell it, well, what value for x do you want me to substitute into the equation and give you a value for. So we're just going to go through here and we're going to systematically enter any of these values until I come up with a 0. Because remember, if I have a root or an intercept or a solution, that becomes a solution, or I know it's a solution when I plug in a value for x and I get back a value of y, 0 for y. So let's just start by putting in a 1. And we found out that when x is equal to 1, y is equal to 0, and that right there means I have a root for this polynomial. So rather than going through and putting this big long list in ourselves and doing it by hand, we're going to use the table function to do what I would call some of the grunt work in this. Now let's go back over here and let's say, okay, so I know that when x is equal to 1, I have a root, and that came from the table, and I can write that in my factored form to look like x minus 1. So this is the root, or this is where it's actually crossing the x-axis, and this is what it looks like in its factored form. Once we've identified one of the roots of this polynomial, we use synthetic division to simplify this polynomial just a little further. So if it's been a while since you've used synthetic division, let me show you or remind you how it is set up. We start by taking this root here and we write it kind of with an inverted L shape like that. Now everything to the right of that comes from, and I'll scroll up here, it comes from the coefficients only of my polynomial. So I'm going to bring down a 2 plus 11x, or excuse me, 11 minus 7 and a minus 6. So that's where those numbers are coming from. We leave a little space and then draw a line. So when we do synthetic division, we're only interested in the coefficients, and the process that we use is basically multiplication and add. So I am going to multiply 1 times 2, and I get 2, obviously. And then I'm going to add straight down. So 11 plus 2 would give me 13. Then I come back and I say 1 times 13. Well, that is 13. And then we add straight down, giving me 6. And it's just repeat. 1 times 6 is 6. We add straight down and we get 0. Now, if you don't get a 0 right here, then we've done something wrong. Go back and check your math, but ultimately you want to get a 0 right here. Synthetic division is basically taking the polynomial and reducing it by 1 degree. So in other words, if I divide 2x cubed by an x, I end up with 2x squared, right? So these are the coefficients now of my new polynomial that's been reduced by a power of x minus 1. So let's rewrite my polynomial so it looks like my original root that we discovered, x minus 1, times this new term right here. So each of these are the coefficients of the term that is 1 less than what we started with. So this is 2x squared plus 13x plus 6. Okay, so 2x squared plus 13x plus 6. Now we're trying to ultimately get this entire thing completely factored. So if I'm looking at just this portion right here, my new term that I just created or found, you want to ask yourself, can I factor that? Can I reduce this or split this up any further? Generally, in a quadratic like this, we can use the properties that we've learned in previous classes to either separate this using trial and error or do the quadratic formula to be able to factor. Now I know that I can factor this guy into a 2x and an x. I know because this is a positive sign that I have to have 2 of the same, and this tells me I need to have 2 positives. So I'm looking for the factors of 6 that will combine with a 2 to add together to give me 13. And so I'm going to try just a 6 and a 1. And then when I check my outer term and my inner term to make sure that gets me the middle, I get plus 12 plus 1 gives me back the 13. So I'm just verifying that I did factor this correct. And I did. And so we have reduced this then down into the smallest factorization that I can. It is completely factored, and it would look like this. F of x is equal to x minus 1, 2x plus 1, and x plus 6. These are now the factors of the polynomial that we started with, and I could therefore solve this factored polynomial to find its roots. Remember that when we solve it, we basically set it equal to 0 and then take each of these factors, x minus 1 equals 0, 2x plus 1 equals 0, x plus 6 equals 0. So this right here becomes x is equal to 1. This one over here becomes x is equal to negative 1/2. And this one over here, when I subtract 6 to the other side, becomes x minus 6. So two things are occurring here I want to show you. We have this function right here, which is my polynomial written in its factored form. And then we have also these three roots right here, which we then solved for. So make sure you understand the distinction in my vocabulary when you're looking for the polynomial in its factored form as opposed to solving for the roots. And that's how we're going to go about taking any polynomial and simplifying it down to finding its real roots or its real zeros.